All right, welcome to The Explainer. Today we are jumping right into the invisible forces that hold our entire world together, chemical bonds. I mean, from the salt on your table to the very air you breathe, it all comes down to how atoms connect with each other.
Have you ever really stopped to think about that? Seriously, what stops everything from just disintegrating into a big, messy soup of atoms? The answer is the chemical bond. It's basically the universe's superglue.
Here's the thing. Most individual atoms are, well, they're just not happy on their own. They're unstable, a little frantic, and they're on this constant quest to find stability, to get to a calmer, lower energy state. Kind of like they all want to be like the super chill noble gases on the periodic table.
So how do they find that stability? For most of them, there's one main goal, and it's called the octet rule. You can think of it as the ultimate atomic ambition, to get a full outer shell with 8 electrons. That's the magic number, and it drives almost everything we're about to see.
To get that full shell, atoms have two main strategies. They can go the dramatic route and just steal electrons from another atom, that's an ionic bond, or they can cooperate and share electrons, which makes a covalent bond. So it's a choice between theft and teamwork. Let's check out the theft first.
Okay, ionic bonds. This is where it gets interesting. We're talking about atomic larceny, where one atom literally rips an electron away from another. But it's all for the greater good of stability.
And here's why that matters. When an atom loses an electron, it becomes positively charged. The one that gains it becomes negatively charged. And what do we know about opposites? They attract. That powerful magnetic-like pull is the ionic bond.
The perfect example of this is regular table salt. Sodium has 1 electron it's just dying to get rid of, and chlorine is just 1 electron short of being full. So sodium gives its electron away to chlorine. Sodium turns positive, chlorine turns negative, and bam! They snap together in this incredibly strong grip, forming a stable crystal.
But what if neither atom is strong enough to just steal an electron? Well, in that case, they have to learn to cooperate. And this brings us to covalent bonds, where sharing is the name of the game.
A covalent bond is just what it sounds like. Two atoms decide to share one or more pairs of electrons between them. This way, both atoms get to count those shared electrons toward their full shell. It's a total win-win situation.
Let's look at the simplest example there is, a hydrogen molecule. Each hydrogen atom has 1 electron, but it wants 2 to be stable. So they team up. They share their single electrons, forming a pair that orbits both of them. Now, each hydrogen feels like it has a full shell. It's a perfect partnership.
The guy who really cracked this whole code was the chemist G.N. Lewis. He was the one who figured out that this whole bonding thing was just about atoms trying to get a full outer or valence shell. And he even came up with a brilliant way for us to visualize it.
And that brings us to Lewis structures. You can think of these as the actual architectural blueprints for molecules. They're simple maps that show us exactly how atoms are connected and where all the important electrons are.
Let's build one really fast, using formaldehyde. The process is pretty straightforward. Count up your electrons, arrange your atoms, hook them up with single bonds, add any leftovers, and then shuffle things around until everybody's stable. First, let's count. Carbon brings 4 electrons. The 2 hydrogens bring 1 each, so that's 2. And oxygen brings 6. Add it all up, and our total electron budget is 12. Next, we put carbon in the middle and connect all the other atoms to it with single bonds. Each bond uses 2 electrons, so we've just used up 6 of our 12.
Now we place our last 6 electrons on the oxygen atom. So let's check our work. Oxygen is happy with 8 electrons. The hydrogens are happy with 2, but hold on. Look at carbon. It's only got 3 bonds, which is only 6 electrons. It's not stable. We've got a problem.
And here is the elegant solution. Oxygen shares one of its extra pairs of electrons and forms a double bond with carbon. Now let's check again. Carbon has 8 electrons, oxygen still has 8, the hydrogens are good, everybody has a full shell, it's a perfect stable molecule. Of course, just when you think you've got the rules figured out, chemistry loves to throw a curveball. That octet rule? It's really more of a strong guideline. Some atoms are total rebels.
You've got two main types of rule breakers. On one side, you have atoms like boron, which can be totally stable with only 6 electrons. On the other side, you've got bigger elements like sulfur that can use extra orbital space to hold more than 8 electrons, sometimes as many as 12.
So let's do a quick fire recap. Bonds are the glue that holds atoms together. Atoms do this to get stable, usually aiming for 8 electrons. Ionic bonds are about stealing electrons, covalent bonds are about sharing them, and Lewis structures are the blueprints that let us see how it all works.
So just stop and think about that. This really simple dance of giving, taking, and sharing electrons. It builds everything. The salt on your food, the water you drink, the DNA inside your cells. Which really makes you wonder, what other amazing things are these simple rules building out there, right now, across the cosmos?